Okay, so we've been talking about techniques of integration. We had one lecture on basic ideas, fundamental theorem of calculus, plus a review of the substitution method. And then we learned about integration by parts. And then last time we learned about trigonometric integrals, how to integrate powers of sine and cosine, or maybe tangent or secant. Um, and also trigonometric substitutions. There are certain integrals with square root sign, which are not easy to do. If regular substitution doesn't work, if regular methods like integration by parts doesn't work, we usually try trigonometric substitution. I'm going to show you a couple of more problems to get added practice, and then we'll talk about uh, the method of partial fractions, which is, I mean, it's basically algebra. It's more algebra than calculus. That's the method that allows us to integrate rational functions if I have a polynomial divided by a polynomial. Let me remind you that we have one more lecture on integration on Tuesday, but next Thursday, 1 week from now, we'll have the first review. And the Tuesday after that, March, what was it? March 9th, we'll have the first midterm. So what I'm going to do in the next few days, I'll do my best to do it before the end of the weekend. Um, I will post the review sheet on Google Classroom, itemizing the topics that will be on the test with some information on the format of the test. And that also includes a number of practice problems. Next Thursday, which is 1 week from now, I will go over those problems. Uh, we'll see how those problems can be done. But the very important point is that when you take a look at that review sheet, you should sit down and after you review the material or while you're reviewing each topic, try to do the corresponding problem from the practice test that I post. So I want you to work on those problems before you show up uh, for the review session on Thursday. It's not going to do you much good if you just show up and listen to what I say about those problems. It's um, it's a whole lot different if you think about those problems ahead of time and then uh, compare your solutions to um, my solutions when I go over them. So that's the plan for the next week or so. Again, I will give you detailed information about the midterm, the format of it, the practical aspects, which is going to be on WebAssign. It's March 9th. It's on the course syllabus. All right, so let's not spend more time on this. I'm going to start doing a couple of practice problems. This is from the previous material. So we saw a couple of, more than a couple of examples of trigonometric substitutions last time. I would like to do two more problems that one way or another, they depend on trigonometric substitution. The first one doesn't look like a trigonometric substitution problem. It's a geometry problem. Show that the area enclosed by this ellipse, the ellipse whose equation is this, x squared over a squared plus y squared over b squared equals 1. This is the ellipse in the plane, which goes from negative a to a along the x-axis. So it has a major axis or a horizontal axis, doesn't have to be major, a horizontal axis extending from negative a to a, and a vertical axis extending from negative b to b. Such an ellipse has this Cartesian equation, x squared over a squared plus y squared over b squared equals 1. We want to show that the area of this ellipse is pi times a times b. Now, in the very special case, a and b are equal. So if a and b are equal, this ellipse reduces to a circle of radius r. And this formula becomes pi a squared. So if a and b are equal, this ellipse becomes a circle of radius a. So r is a or b, because they're equal. And this formula reduces to pi a squared, which is the good old formula for the area of a circle. So this is, you can think of it as a generalization for the formula for the area of a circle. So the idea is to figure out the formula for this graph. If I can figure out what the formula for this graph is, y equals something in x, then if I integrate that from negative a to a, that's going to give me the area under that graph. And then I double it, I get the total area of the ellipse. And because of the symmetry, I can even simplify this further. I can integrate that function, whatever this function is, I don't know. But I can integrate that function from 0 to a. That will give me this area, which is, by symmetry, a quarter of the total area of the ellipse. I find the answer, then I multiply it by 4. So it all boils down to figuring out the formula for the upper half of the ellipse. And for that, I have to take this equation and solve it for y. So if I solve this equation for y, I'm going to end up with something like y equals blah, 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 something in x. And that's going to be the formula for that part. So let's see how it develops. So solve for y. So we'll see how this problem will lead us to some trigonometric substitution. So wait for that. So if I solve for y, y squared over b squared will be 1 minus x squared over a squared. In other words, it's going to be a squared minus x squared over a squared, if you take the common denominator. And now, so that's y squared over b squared. In order to recover y, I multiply each side by b squared. So I put a b squared here, and I get rid of this. That's going to be y squared. And then I take the square root. So if I do the simple algebra, it follows that y will be plus or minus b over a square root of a squared minus x squared. This is a simple algebra, algebraics that you can make. Now I get two solutions. One of them is plus blah blah blah. The other one is minus that. And that's an indication that if I take the plus sign, that's going to give me the graph. The graph of the plus sign will be the upper ellipse, and if I take the negative sign, that's going to describe the lower semi-ellipse, just like the case of the circle. So since I'm interested in the upper one, doesn't matter. I could have taken the lower one, but so I take the plus sign. That's going to describe, that's going to be the formula for the upper. So this is the upper semi-ellipse. That's the graph of this part, the top part. Okay, so I have this function, and now I can say that the area of the ellipse So the area of the ellipse is 4 times this area, right? It's enough to compute this area and then multiply it by 4. And what is this area? This area is the integral from 0 to a of this function. It will give me the area under this graph. So it's going to be 4 times the integral from 0 to a of this function, b over a square root of a squared minus x squared dx, which is 4b over a. B and a are positive constants. I can pull them out. Integral from 0 to a of square root of a squared minus x squared dx. So now you see that when I write the formula for this area, it leads me to this integral. And this is one of the forms that we discussed last time. Whenever you have square root of a squared minus x squared, well, if you have an extra factor x outside, then obviously the best way is the u substitution. Call a squared minus x squared the new variable u, then perform the integral. In some simple cases, you can just do the integral with a more elementary method. But usually, if you have an integral involving a squared minus x squared, the method is a trigonometric substitution. And what was the suitable trigonometric substitution? It was the one that after applying, it would let me get rid of this radical sign. So if you remember, for this, the appropriate trigonometric substitution, trig substitution, was a sine theta. The reason being, if I put a sine theta here, x squared will be a squared sine squared, factor a squared. What's left is 1 minus sine squared, which is cosine squared, and cosine squared under the square root, it'll come out. It'll become cosine. It's absolute value of cosine, but because of the range, it's positive, so we'll see. So if x is a sine theta, I need dx. Oops, dx is a cosine theta d theta. Now, let's also figure out the corresponding bounds. You see, x is between 0 and a. So since x is between 0 and a, I have to figure out the corresponding interval for theta. When x is 0, look at this relation. When x is 0, sine theta must be 0, so theta is 0. And when x is a equals a sine theta, so cancel a, that means sine theta must be 1, and therefore theta is pi over 2. So while the interval for x is negative is 0 to a, after this substitution, the interval of the new variable theta becomes 0 to pi over 2. And therefore, after this substitution, I'm going to end up with the new integral. So I had 4 b over a outside. Then it becomes integral from 0 to pi over 2. This thing, I can write it, but I mean, this is something. Yes.
How did you get pi over 2 again?
If x is a, you see the upper bound. If x is a, put a here, then a equals a sine theta. So cancel a. That means sine theta must be 1. And sine of theta being 1 implies theta is pi over 2. Take arc sine or sine inverse. So does that answer your question?
Yes, thank you.
Good. Okay, this step is something you should be able to do in your head. It's not really difficult, but this time I'm going to write it down. But every time you perform a trigonometric substitution, this happens. So I'm writing it down, but really you can do this all in your head and skip that step, because we know that if we put a sine theta here, this thing will become a squared cosine squared. It comes out of the radical. It will become a cosine theta. But let me write it down. And then I have dx, which is a cosine theta, d theta. That's dx. And now look at this. This thing is a cosine theta. Again, under the radical, if you factor a squared, you're left with, so factor a squared and bring it out, it becomes an a. So that's your a. And then what's left is 1 minus sine squared theta. 1 minus sine squared theta is cosine squared theta. Square root of cosine squared is absolute value of cosine theta. But theta is between 0 and pi over 2, so cosine is positive. So absolute value of cosine, you don't need absolute value. So this thing simplifies to a cosine. So let's see. Let's clean up. I've got an a here, another a here. So that's a squared. I can put it outside. And I have a squared, and I have one a on the bottom. In other words, I can, for example, I can say that this a cancels one of these a's. And then what that gives me is outside I get 4ab, and then integral from 0 to pi over 2 of, I have a cosine theta coming from that radical, and I have a cosine theta coming from dx, so that's cosine squared. So after that trig substitution, I'm going to end up with this integral of cosine squared, which is something we've seen before. What was the trick? If I have odd powers of sine and cosine, I save one factor, and I write the remaining factor, which now has even power in terms of sine squared or cosine squared. I do a substitution, a u substitution. If I have even powers of sine and cosine, the trick was to use the doubling angle formula. Write cosine squared of theta in terms of cosine twice theta. This is the first technique that we learned last time. So this is 4ab, integral from 0 to pi over 2. Instead of cosine squared theta, I write 1 plus cosine 2 theta. This is one of the few identities that you need to know. It's very useful. If you remember the list of few identities that I wrote in my course notes last time, there were like 4, 5. This was one of them. And now this is easy to integrate. So you can bring this 2 out. This 2 on the bottom, bring it out. With this 4, it leaves you with 2ab. And then what is the antiderivative of, so I've already taken care of this 2. So what's left inside the integral is this. And now I'm trying to find antiderivative. Antiderivative of 1 is theta. Antiderivative of cosine 2 theta is 1/2 sine 2 theta. So that's the antiderivative of 1 plus cosine 2 theta. And then I have to evaluate this at pi over 2, and then 0, and then subtract. So let's see what you get. I'm just going to say it because it's easy. If I put pi over 2 in here for theta, I get pi over 2 here. And this will become pi. Sine of pi is 0. So the second term won't give me anything. I will just get pi over 2 from this factor. And then when I plug in 0, this will be 0, and this will be 0, so I won't get anything. So the total effect is just having a pi over 2 here. That's the only surviving term. And this will be pi ab. That's the thing we wanted to prove, right? We wanted to show that the area is pi ab. So this is a generalization. At the same time, we reproved or proved for the first time, if you haven't seen it before, that the area of a circle of radius r is pi r squared. Because in the very special case a and b are equal, this reduces to a circle. So this is a good example in that it involves a bunch of integration techniques that we have discussed before. None of them is difficult, but I mean, you need to get, like I said last time, you need to gain enough experience to be able to see what method you are better off choosing for each specific problem. And again, my goal is not to try to torture you by giving you a hard integral, because that's not going to prove anything. So my goal is not to give you the most difficult, the trickiest integral to see if you can do it. That's not the idea. The goal is to be able to learn the basic ideas of integration. If the integral is too complicated, later on in your other courses, if you have a complicated integral, you can always look it up in a table. But you have to know the basic ideas. Like I said in the beginning of the lecture, we'll discuss exam later, and I will give you a review sheet with some information. So, all right, let's do one more problem. We have a lot to talk about, the new method of partial fractions. So let me remind you of two useful integral formulas. One of them is the integral of tangent. This is something I told you about last time. If you write tangent as sine over cosine, then apply a u substitution, u equals cosine, you can perform that integral easily. And you're going to end up with minus ln of absolute value of cosine, which you can also write as ln of secant of x. So this is something that we talked about last time. There is a companion formula, the integral of secant. And it turns out that using a similar trick, you can show that integral of secant is ln of secant plus tangent in absolute value. Okay? So, for example, if you want to know why, take the derivative of this side. You see that when you simplify it, you get secant. Derivative of this will be derivative of ln of secant plus tangent will be derivative of this divided by itself. Ln of u has derivative u prime over u. What is the derivative of this? Secant x tangent x plus secant squared x. And when you divide that by secant x plus tangent x, you factor a secant x from the top. Two big terms will cancel out, and you're left with secant. So it's easy to check. These are useful. I mean, I can't say that, especially this one, I can't say that this is something that you should definitely memorize. No, but right now that we're in the middle of integration, it's a good idea to remember this as one of the useful integrals. But later on, I mean, even a lot of mathematicians don't necessarily remember this formula because things like this, mathematicians tend to use their precious memory for more important stuff, and then if they need it, they always derive it. So this is one of the integrals that right now that you're taking this course and you're in the middle of doing integrals, it's a good idea to remember it, but it's not something that you should definitely keep in mind always as part of your mathematical knowledge. Okay, let's do this problem, this integral. 1 over square root of x squared plus 25. If it were 25 minus x squared, so before I do this, let me just ask you this. If I had square root of 25 minus x squared, what would you do instead of this, if I had this? Please say it.
Sine theta.
Very good. So either you would do, so you would choose x equals what? The trigonometric substitution, x
Sine
equals
theta.
sine theta, almost.
A sine theta.
What is a?
5.
5. Good, because this is supposed to be a squared. So you would do x equals 5 sine theta. And then that trigonometric substitution would simplify this. Or you could even remember that this is a slight variation of the arcsine integral. If you go back to the first integration lecture, I told you that this is sine inverse of x over a. So if instead of x squared plus 25, you had 25 minus x squared, it would be a piece of cake. It would be much easier. Because this is the type of integral, this would have been the type of integral we've seen before. But this is a different problem. It's x squared plus 25. And as such, we need a different method. And that method is the trigonometric substitution, which is, what the heck is that? Trigonometric substitution, which is, I'm going to call x 5 tangent of theta. And then my dx will be 5 secant squared theta, d theta. Whenever you have integral of a squared plus x squared, in other words, I'm sorry, whenever you have the integral of square root of a squared plus x squared, or x squared plus a squared, the suitable trigonometric substitution, if you want to choose a trigonometric substitution, the suitable choice would be a tangent theta. Because look at this. If I now pick 5 tangent theta and put it here for x, this will be 25 tangent squared plus 25. Factor 25, what's left is tangent squared plus 1. And tangent squared plus 1 is secant squared. So you get a perfect square under the radical. When you take the radical, you get rid of that square root sign. Okay, so let's perform this. So the integral will be, so on the bottom I have $25. Again, this is something that you should be able to easily do in your head, this step, but since this is, I'm trying to explain everything in detail, I'm writing down every single step. And then dx is, oh, I'm sorry, 25. 25 tangent squared theta plus 25. And then dx is 5 secant squared theta, d theta. And now this thing, again, this thing is 25. If you factor 25, tangent squared theta plus 1, which is secant squared theta. And then since I'm taking the square root of this, the square root of that will be 5 times secant theta. So I have 5 secant theta on the bottom. It cancels a 5 right here. And one of the two, one factor of secant theta on the top. So I cancel 1 secant theta on the top with 1 secant theta on the bottom. You know what? Because I don't want to, I want to make sure this is not confusing later on. Let me just make sure everything is perfectly under the radical. It's covered by this. And let me just write that the whole thing after you take radical will be 5 secant theta after you bring it out. And now that 5 secant theta on the bottom cancels the 5 secant theta on the top, and you're going to end up with the integral of secant theta d theta. So it simplifies a lot. That's the only thing that survives, the integral of secant theta. What is the integral of secant theta? Well, I just gave you the useful formula. Integral of secant is ln of secant plus tangent. So this is going to be ln of absolute value of secant theta plus tangent theta plus a constant. Now, we got the answer, but my answer is expressed in terms of theta. There was no theta in the original problem. I have to express my answer in terms of the original variable x. So somehow I have to plug in for theta in terms of x and simplify. So do I know what tangent theta is in terms of x? Yes. Tangent theta times 5 is x. So tangent theta is x over 5. That's easy. I know what tangent theta is in terms of x. It's just x over 5. Do I know secant theta in terms of x? Yeah, I can calculate it. So I can either do it using simple trigonometry in my head, because I know the relation between tangent and secant, or I can refer to this favorite method of using test triangles. Draw a little test triangle, call an angle theta, and now what you know is tangent of theta. What you know is tangent of theta is x over 5, right? X over 5. And you would like to know secant of theta. What is secant of theta? If tangent of theta is x over 5, what is secant of theta? So label this picture. Tangent of theta is x over 5. That's opposite over adjacent. This ratio must be x over 5. So you can put any two numbers here whose ratio is x over 5. What's the easiest choice? Putting x here and 5 here. Doesn't get easier than that, right? Tangent of theta is x over 5. And now secant is 1 over cosine. So secant is hypotenuse over adjacent. So I need to know this length. And in this triangle, it's clear that this length by the Pythagorean theorem is square root of x squared plus 25. So it follows that secant of theta is square root of x squared plus 25 divided by 5. Cosine would be 5 over square root of x squared plus 25. Secant is the reciprocal of that. So now I know both tangent and secant of theta in terms of x, so I'm going to plug them in. It's not going to be a good answer if you just leave it like this. You'll have to go back to the original variable and express the answer in terms of x. So it's going to be ln of square root of x squared plus 25 divided by 5. That's secant theta plus tangent theta, which is just x over 5, plus a constant. So that's a perfectly legitimate, correct answer. So I don't want you to worry about simplifying this further. But for those of you who pay attention to these things, just let me mention that I can further simplify this, because this can be written as ln of square root of. So this last step is not necessary. I'm just saying it for the record. Plus x. You see, if I take common denominator here, it's going to be this plus x, the whole thing divided by 5. And then ln of something divided by 5 is ln of that thing minus ln of 5. Minus ln of 5 is just a constant. I can absorb that into this constant. So plus a different constant. So anyway, that 5 on the bottom of the whole thing inside the logarithm doesn't change the function. It just changes the function up to a constant. And since everything is up to a constant anyway, I can take that extra constant and lump it together with that c. So it's even easier to look at now. This will be the answer. Again, if you write the answer like this, it's perfectly okay. It's not, so I don't want you to stress over that. All right, so we spent almost half an hour, a little more than half an hour, on practicing older stuff. And now the remaining part of this lecture will be on another technique of integration, which in some sense, it's even more elementary than integration by parts or trig substitutions. And so this is about how to integrate rational functions. Rational functions means a polynomial divided by a polynomial. So you have a polynomial on the top, a polynomial on the bottom. The ratio of these two, we want to integrate it. So that's the topic. And the classical method to deal with the integrals of rational functions is the so-called method of partial fractions. I'll explain what that means. Integration by partial fractions. That's the topic. So the goal is to integrate rational functions of this form. So rational, remember that a rational function by definition is the ratio of two polynomials. So for example, x squared plus 1 on the top, x cubed minus 2x squared plus 5x plus 7 on the bottom. Not every ratio of two functions is a rational function. So if you have sine x divided by x, even though that's a fraction, it's not a rational function because sine x is not a polynomial. So we're P and Q are polynomials. So what is the idea? I'm going to teach you the general idea through a series of examples of increasing difficulty. We'll start with very simple examples. But the general idea is this. Let me say it right at the outset. The general idea is take your rational function. Are you listening to me? This is important, maybe even more important than the formulas. It's important to know what we're doing. Take your rational function and look at the denominator. Try to factor the denominator. It's a very algebraic method. Most of it is algebra. Factor the denominator into as far as you can. So either you get a bunch of linear factors like x plus 1, 2x minus 3, and so on, or sometimes you get quadratic factors which cannot be factored anymore, like x squared plus 1. So factor the denominator, and then try to write this rational function as sum of a bunch of simple fractions, each of which has one of those factors as the denominator. In some sense, this is the inverse of taking common denominator. So the goal is to think of this rational function with a bunch of factors on the bottom as the result of taking common denominator of the sum of simpler fractions. So we have the final answer. We want to figure out what those individual fractions were. Once we split this, and this is what's called partial fraction. That's the reason for the name. Once we write our rational function as sum of simpler rational functions, each of which having a linear or quadratic bottom, then it's very easy to integrate them. So I would say this method is like maybe 70, 80% algebra at the level of high school algebra, and I don't know, 20, 30% calculus. So let me show you how this method works by a bunch of examples. Now, the first example is not really an example because it's very simple, but we're going to use it in the upcoming integrals. So I'm going to talk about it. What do I have? So let me take a look at the examples that I have here. How about this? 1 over 3x plus 2. Now, this is as simple as it gets. It's a rational function. The top is just a constant 1, and the bottom is a single linear term, 3x plus 2. So for this, I mean, I could have given you this problem 2, 3 lectures ago. Can you tell me what to do? What would you do if you had 1 over x? Are you thinking, or you're not even paying attention? Thank you. Yeah, if it were 1 over x, the integral would be ln of x. This is not 1 over x, but still 3x plus 2 is not a complicated thing. It's just a linear term. So what do you suggest? Is there any way I can simplify this by perhaps a substitution? If I told you that a u substitution, very good. 3x plus 2. Yeah, exactly. So this is a simple substitution. Call u 3x plus 2. du will be 3dx. So after this substitution, you get integral of 1 over u, and dx is 1/3 du. So this is 1/3 of integral of 1 over u, which is ln of absolute value of u plus a constant, which is 1/3 ln of absolute value 3x plus 2 plus a constant. So really, at this point, this should be a very easy problem. So 1 over a linear function of x, which might be considered as the simplest type of a rational function, is easy to integrate because it's basically ln of the bottom. So as you see, the answer is ln of the bottom. But because of 3, I have to modify it by a 1/3, because after differentiation, if I don't put this 1/3 here, I get an extra 3 in front of it. So there is nothing so special about 3x plus 2. If I had ax plus b for any linear term on the bottom, so similarly, if I have the integral of 1 over ax plus b, where a and b are numbers, dx, this would be 1 over a. I'm assuming a is non-zero, because if a is 0, then it's just a constant. So that's even. 1 over a ln of absolute value of ax plus b plus some constant. So I want you to observe how simple this case is. And this case will be a sort of stepping stone in dealing with more complicated cases of rational functions. So is everybody happy with this? I just want to make sure that you feel comfortable about this very simple case. The fact that very few people told me what to do, it just gives me a little bit of a pause that maybe we're not all on the same page. Was this example clear? Yeah, exactly. All right, so whenever I have a single linear term on the bottom, I know how to integrate. It's going to be something like this, and it's basically ln of the bottom, but with this constant in front. So for example, if I integrate 1 divided by 5x plus 7, that will be 1/5 ln of 5x plus 7 in absolute value. Okay, now let me give you a first example in which it's not quite as simple looking at this, but we can reduce it to this case. And that is the essence of the method of partial fractions. So what I have is 2x plus 1, x squared minus 2x minus 3 dx. Now, the first thing you observe is that this is a rational function. So we're trying to integrate a rational function. If the top, you see, you always start with the simplest possible method. The simplest being, ask yourself this question: do I know what the answer is right away using the basic table? If not, does U substitution work? If not, can I try integration by parts? If not, depending on the form of the integral, would a trigonometric substitution help? Or, since this is a rational function, maybe integration by partial fraction will help. If the top was 2x minus 2, which is exactly the derivative of the bottom, the derivative of the bottom is 2x minus 2. If I had that on the top, it would be a piece of cake. I would call the bottom u, and then the derivative du would be 2x minus 2 dx. So this would be very simple. But unfortunately, it's not like that. So what I try is I take a look at the denominator, and I start by trying to factor the denominator. It's very easy to factor the denominator here, as you can see. So again, the goal is not to give you really complicated problems with gruesome algebra. So in this example, I give you something which factors easily. Can you tell me the factors?
X minus 3, x plus 1.
Very good. All right, so these are the factors. Now, in order to integrate this function, I momentarily forget about integration, and I just do algebra. What do I mean by that? I take this fraction, and I ask myself this question. This fraction has 2 linear factors on the bottom. Is it possible to write this fraction as a number divided by x minus 3 plus another number divided by x plus 1? Is it possible to split this fraction as sum of 2 fractions, each one having one of the linear factors on the bottom? This is reasonable because if somebody gave you such a sum and they ask you to combine them, you would take the common denominator, and the denominator would be the product of these two, and then you would simplify the top. So in essence, you would be getting something which would look like this. The question is, what are the appropriate numbers A and B for which this holds? So the question is, find A and B. These are two numbers such that this holds for all x. I want to put suitable numbers A and B here such that the left side is equal to the right side for every x. So how can I determine A and B? It's very easy. Take the common denominator here. The bottom will be x minus 3 times x plus 1. Figure out the top and set it equal to this top. And then out of that, you can find A and B. So bear with me. In other words, another way of saying it is that you can multiply both sides of this identity by x minus 3 times x plus 1. On this side, you get 2x plus 1, which is the top on the left side. And on this side, you get a times x plus 1 plus b times x minus 3. Is everybody happy with this? I just combine these two. The bottom is equal to this bottom, and the top will be a times x plus 1 plus b times x plus 3. That would be the top. And I set it equal to this top. Another way of saying it is, now that these two are supposed to be equal, I multiply both sides by this thing, by x minus 3 times x plus 1. On the left side, I'm left with the top. On this side, when I multiply by x minus 3 times x plus 1, x minus 3 cancels this x minus 3, so I'm getting a times x plus 1. And when I multiply this by x minus 3 times x plus 1, x plus 1 cancels out, and I get b times x minus 3. So this is supposed to be an identity for x. It is supposed to hold for every x. And my goal is to figure out which A and B will do that. OK, I'm going to show you two different methods to recover A and B. And the first method is the simplest method. You say 2x plus 1 equals, multiply out everything, ax plus a plus bx minus 3b. Collect similar terms together. So collect x terms together. That's a plus b times x. And collect constants together, a minus 3b. So you see on the right side, I multiplied out everything. And then I lumped x terms together. That's this. And I lumped constants together. That's this. OK? Now, look at this. 2x plus 1 is supposed to be equal to blah times x plus another blah for every x. So that means the coefficient of x here must be 2, and the constant term here must be 1. So you equate coefficients of similar terms in x. If you had x squared, then you would equate the coefficients of x squared. So out of this, this is the first method, of course. I'm going to show you another method. So out of this, it follows that since this holds for every x, the similar coefficients must match up. A plus b must be 2, and a minus 3b must be 1. And what does that tell you? This is a simple system of two equations and two unknowns. For example, if you multiply the first one by 3, and then add the two equations, 3b and minus 3b will cancel out, 3a. So let me write it like this. So if you multiply this by 3, this equation multiplied through by 3, then 3b, and then add the two equations. 3b and minus 3b cancel out. 3a plus, that's 4a equals 7. So A will be 7 over 4. And then, for example, put it here. B is A minus 2. So B is 7 over 4 minus 2, which is minus 1/4. So that gives you the value of A and B. That's one method. In other words, one method for finding. So once you reach this identity, in order to recover A and B, one method is to lump similar terms and powers of x together and then equate the coefficients of similar powers of x. Another method, which you may find easier in this case, is, so let me show you another method in order to recover A and B.
Wait, does the B should be positive, not negative?
You're right. It's plus 1/4. Thank you. Yeah. Thank you. So another method. What is this method? Remember, we had this identity, and we wanted to recover A and B. This identity is supposed to hold for every x. No matter what x is, they are supposed to be equal. So what if I choose particular values of x? And of course, I'm not going to choose, I don't know, 73 for x, which is kind of irrelevant. I can choose anything I want, of course. But what is the clever choice? The clever choice, for example, would be x equals 3. If you choose x equals 3, this will be 0. So you get rid of this b term altogether, and you can recover A. And then how do you recover B? By setting x equals -1, you kill this term, and then you recover B from the resulting equation. So the second method is to choose clever choices, to make clever choices for x, plug them in, and find A and B. Why can I do that? Because this is supposed to hold for every x. So in particular, holds for x equals 3 or -1 or anything for that matter. So if x is 3, so substitute x equals 3. On the left side, you get 7. On the right side, you get A times 4, otherwise known as 4A. And this term, the B term, will be wiped out, because x minus 3, if x is 3, is 0. And that gives you A equal 7 over 4. And then choose -1 for x. That will kill this term. On the left side, you get -1. On the right side, you get minus 4b. And that means b is 1/4. Of course, the same answer. Either way, look at what we have achieved. So still, we're doing algebra, very simple, low-level algebra. So what we have achieved is the splitting of this term. Remember, this is what I tried to do. I tried to take my original fraction and split it as a number divided by x minus 3 plus a number divided by x plus 1. And now I know what A and B are, so I can put 7 over 4 for A and 1/4 for B. In other words, in a much more respectable way to write. This is 7 over 4 times 1 over x minus 3 plus 1 over 4 times 1 over x plus 1. So this finishes the algebraic part. I succeeded in splitting my original fraction into sum of two very simpler fractions. Why is this useful for the purpose of integration? You may ask. This is just too many terms, and this looks much more compact and pleasing to look at. Well, yeah, but when it comes to integration, this form, this partially fraction form, is much easier to integrate, because basically I have to integrate 1 over x minus 3, which is ln of x minus 3, and I have to integrate 1 over x plus 1, which is ln of x plus 1 in absolute value, and that's it. And therefore, the integral of this guy dx is 7/4 the integral of 1 over x minus 3, which is ln of absolute value x minus 3, plus 1/4 of integral of 1 over x plus 1, which is ln of absolute value x plus 1. At the very end, we put a plus c. So I've been using this simple fact that we established before. Whenever I have 1 over some linear term, I can integrate it. The integral is basically ln of the bottom, but I have to put 1 over a in front of it. If a is 1, then that's going to be 1. So that's why you don't see anything here. OK.
Professor?
Yeah.
Quick question. So just to clarify, when you're integrating the top, the 7 over 4 times 1 over x minus 3, so you're able to separate those two terms that are adding together and integrate individually?
Mm-hmm. That's what we did. Instead of this one fraction, whose bottom is the product, we split that into the sum of two fractions, each one receiving only one linear term on the bottom. That was the main idea. Yeah.
So you would write like integrating 7 over 4 times.
Exactly. So the integral of this will be integral of this plus integral of this. Of course, these are constants. They can be pulled out. So essentially, I have to integrate 1 over x minus 3 and integrate 1 over x plus 1. Yeah.
Thank you.
And I add them up because this is now a sum. OK, let's take a 5-minute break. We will continue this discussion by making it, we'll consider variations of this method, because not every fraction can be split. When you factor the bottom, you don't necessarily get a product of distinct linear factors like this. Quite possibly, maybe a factor repeats. Maybe some of the factors repeat, so you have something squared or something cubed. Or maybe some factors are irreducible, quadratic, that you can't factor anymore, like x squared plus 1. X squared plus 1, you can't factor anymore. So we'll see how to deal with those cases. OK? See you in 5 minutes.